My dear participants, I shall continue with fitting of the four models. M1 NLS, it is on the iron slag data. It is chemical versus beta naught plus beta 1 into magnetic. So, it is the simple linear regression model, but we are fitting with NLS, non-linear regression. So, you start list is equal to beta naught is equal to 8 and beta 1 is equal to 0.5. And when we run this command, we get the summary of results. Summary of results give, this is the formula, and this is beta naught estimate is 8.95, standard error is 1.65. When you divide this estimate with the standard error, its t value is 5.40420 and p value is this. So, that means p value is less than 0.05 and that indicates that beta naught is significant. Similarly, beta 1 0.5 and standard error is 0.07. If we divide this by this, the value is, the t value is 7.695 and p value is 4.38 into 10 raised power. So, that means the p value is much less than 0.05. So, that means beta 1 is also significant. And then residual standard error, this is, and see, since there are two parameters beta and beta 1 to be estimated, so that is why degree of freedom is 51 minus 3. Fitting quadratic model. In fitting quadratic model, basically the function is again NLS, chemical versus beta naught plus beta 1 into magnetic plus beta 2 into magnetic square. Actually, magnetic method is much easier than chemical method, and that is why chemical has been taken as response variable and magnetic method is treated as input variable. So, here we have, here the expression is like this. It is y is equal to beta naught plus beta 1 x plus beta 2 x square plus error. So, here this is first insulated and it is square. So, in the insulation it computes first magnetic square and then it becomes the part of the model. So, it is this. So, we are getting the results beta naught, beta 1, beta 2, but here you see beta 2, the coefficient of x square is not statistically significant. So, that means addition of this quadratic term is not beneficial. Fitting model 3, again NLS, and here the model is actually log model. It is chemical versus EXP. If we transform this, see this expression is, we have taken actually here y is equal to e raised power beta naught into e raised power beta 1 into x plus error. So, here this model is being fitted. So, again we are exactly writing this formula NLS chemical versus exponential beta 0 exponential beta 1 into magnetic, and we have started values beta naught is equal to 1, beta 1 is equal to 0.5, and we are getting the results beta naught 2.5 and beta 1 0.0247. Standard error is 0.075. So, if we divide this estimate 2.5 divided by 0.07, the t value is 33. So, which is highly significant. Beta 1 0.027, standard error is 0.003. If you divide this by this, we get 7.45. So it is much less than 2, much greater than 2. So that means it is again a significant T ratio, significantly different from 0. So that means both beta naught and beta 1, they are significantly different. See, fitting M4, here we have fitted the model like this. It is y is equal to e raised power beta naught into x raised power beta 1 plus error. This is again a nonlinear model. So we have fitted this model. In econometrics, these models are very common. So if we fit this model, the estimate of beta naught is 1.2 and standard error is 0.23. If you divide this by this, you get the p value, the t value 5. If it is greater than 2, that means it is significant. So p value is 1.42 into 10 raised power minus 6, and beta 1 is also significant, because if you divide estimate by standard error of the estimate, the t value is 7.97, it is around 8 and it is far away from 2. So 1.5 into 10 raised power minus 10, so it is again significant. So in all these situations, these parameters are significant. Now comparing the three models using AIC. AIC is known as Akaike Information Criteria, which was introduced by Akaike in 1974. Actually, earlier people were talking of R square for model comparison, but R square is nothing but it is SS due to regression divided by SS total. But R square is not a good measure. It is not a good measure. It is often it misleads the quality of fitting. So that's why Akaike information criterion, which was introduced by Akaike in 1974, it is the main method of comparing models, and AIC is nothing but minus twice of log likelihood plus 2k. K stands for the number of parameters. K stands for the number of parameters. K stands for number of parameters. So it is AIC, Akaike information. So since it involves this twice k is the penalty term, and it involves the likelihood involves each observation. So that's why it is a better criteria for comparing the models. So AIC of model 1 is what? Model 1 is nothing but it is simple linear regression model. It gives 286.0531. So it is 286.0531. Whereas if we fit quadratic model, it is 286.6953. It is somewhat increased. So that means the quadratic model is not better than the simple linear regression model, because it is increased, AIC is increased. Lesser AIC, better fitness. Now if we go for M3, that is log linear model, it is 288.515164. So, it is not, model 3 is also not preferable over model 1. But when we talk of model 4, model 4 gives 285.3631. So, that is why it is giving the least value of AIC. So, that is why it is being preferred over the other 4 models. Thus, on the basis of AIC, model M4 is the best model. Looking into graphically, see what we are doing. See, O par is equal to par MF rho C 2 by 2. Actually, MF rho is, there are two functions. Par means graphic parameter setting. O par means graphic parameter setting. And what is graphic parameter? MF rho, it divides the screen into 2 rows and 2 columns, and then figure will be filled row wise because MF row. If here it is MF col, see MF row is equal to C 2 by 2. So, it will divide the screen, output screen, into 2 rows and 2 columns, and figure will be filled row wise. But if it is MF col, then C 2 by 2 again. But here the figure will be filled, it is again 2 by, but figure will be filled first column wise, not row wise, like that. So, this is the difference between MF col and MF row. So, it will divide the screen into 4 figures, and then each command will be, see here, like this is the first window, first panel, then second panel, then third panel, and then fourth panel. So, here then we are plotting. Plot is a high level function. So, it is chemical versus magnetic, data is equal to iron slag, and main title is linear. So, it is linear, and then we are adding lines, these lines, iron slag, magnetic. So, on x axis it is magnetic, on y axis it is fitted values. So, it fits the line, and then we are using another plot. So, that plot will come here because it is MF row wise filling is there. So, MF row, see, plot chemical versus magnetic again. So, it will generate the scatter diagram. Main is equal to quadratic, main title is quadratic. Then lines, iron slag, magnetic, and fitted values by M2. So, this is the quadratic model, this is the quadratic fit. And then we will go ahead, see, we will again come here, plot chemical versus magnetic, data is equal to iron slag, main is equal to semi-log. So, it will generate the scatter diagram, and then we are adding lines, iron slag, magnetic, on x axis, and on y axis it is fitted M3. So, this is the fitted line by using the model M3, and then log, it is log dash log, it is not log, it is log model. So, here see, from the quality of fit, it seems that the best choice is log model. Model 4 suits best, followed by model 1, followed by model 2, followed by model 4. So, this is the ordering of AIC also. So, we have verified the numerically we have seen, and graphically also we are looking into. Like, see here, AIC of model 4 is the least 285, and the model 3 has the maximum maximum AIC. So that quality of fit also supports these facts. So this is the best model from the fitting. Then par O par, actually what we have done, that here par, O par, par, MF row, we have divided the screen into two rows and two columns, and then we want to exit from this. So par O par, it will return to the original settings, one row and one column. On the basis of graphic output, it could be seen that the best fitted model is M4, followed by M1, followed by M2, and finally the last choice M3. These findings are also suggested by AIC values also. The problem of starting values. Choice of starting values is a problem sometimes that can be solved using the function SS-logis for logistic growth model. Similarly, they have developed, the base developer have developed many functions. They start with SS-logis, SS-McMahon. So here we shall use the data ELISA assay of DNAs. The DNA's data frame has 176 rows and 3 columns of data obtained during the development of an ELISA assay for recombinant protein DNAs in the rat serum. So names DNAs, it is in the base package, are run, concentration and density. So density is the response, concentration is the predictor, and run. Using a self-start model. So here first what we have done, DNAs 1 is equal to subset DNAs run is equal to 1. Actually there is run is equal to 1, run is equal to 2, like that. So if we want to select those rows which belongs to run is equal to 1, we can make the command subset DNAs run is equal to 1. So it will select only those data sets which belongs to run is equal to 1 and remaining will be discarded. So FM1 model, fitted model 1, NLS density, SS-logis, this is the logistic growth model, and these are the parameters. These are the parameters of the model. Log of concentration, these are the parameters of the model, and DNAs is the data. DNAs is the data which based on the run 1 only. And summary, so these are the results. These are the summary of results. See, ASIM 2.3, standard error 0.007. If you divide this, you get T value. T value 30 means it is highly significant. It is away from 2. X mid, it is also significant because the T ratio is 18 and P value is 1.22 into 10 raised power 10. And then scale. So all these 3 parameters are significant. So we can compare with 4 parametric logistic regression model. NLS, it is not logistic regression model, it is logistic growth curve model. So here FM2, here subset is equal to 1. Now we have introduced 2 more parameters, A and B and C. These are the results. So introduction of A does not significantly improve the model. So it should be dropped from the model. ANOVA and ANOVA FM1, FM2. So when we compare these models, the P value is 0.6551. That means addition of A does not improve the model. So we find that addition parameter does not improve the model. So this is all about today's lecture. In my next lecture, I shall talk about some further modeling using NLS.